Dear students, welcome to another lecture of Basic Electrical Engineering. In this lecture, we will discuss about the concept of rotating magnetic field in three-phase induction motors. This particular concept is used, or it is the base of the operation of a three-phase induction motor. So, as you know that a three-phase induction motor has two three-phase windings. One is on the stator and one is on the rotor. The formation of rotor can be of cage type, or it could be a wound rotor three-phase induction motor, right? So in both the cases, we have three-phase winding on stator as well as rotor. The connection of three-phase winding could be a star connection or delta connection, depends upon the rating of the three phase induction motor or requirement, as far as the application is concerned, right? Now, as you can see in these three diagrams here, the first diagram indicates the winding connection of a three-phase induction motor. Here we have star connected windings. This is winding A, then winding B, and then winding C, right? And similarly, we have a three-phase winding on the rotor, and then we have an air gap here, right? Now, the three-phase induction motor is known as a self-starting motor. Self-starting means we do not need any starting method to start a three-phase induction motor. It starts automatically, it runs automatically as soon as the magnetic field is set up in the air gap in a three-phase induction motor, right? Now in the second diagram, you can see that we have windings here. This copper wire represent the winding on the stator, and this is the rotor part here, right? Now this phi Y, phi R, and phi B. Now because we are providing supply, three-phase supply on the stator, right? Here we give supply, right? So this three-phase supply produces a three-phase flux in the air gap in a three-phase induction motor. Now this three-phase flux, that means it is a bidirectional flux, time varying flux, and it is a three-phase flux because of the three-phase winding on the stator. Stator winding carries the current from the supply. Now, this three-phase flux has three phasors which are represented as phi Y, phi R, R for red, Y for yellow, and B for blue. You can also understand it with the color coding, right? Here we have a red phasor. This phasor. This one is for the flux produced by the red phase. Yeah, phase one, right? Similarly, we have a blue phasor here, which indicates the phasor of the flux produced by the blue phasor, or you can say phasor 2. Similarly, we have for the phasor 3, right? All these phasors, as you can see here in this diagram, first one, these three windings are placed at 120-degree apart from one another. They have a phase difference of 120-degree, both on stator as well as on rotor. So the same thing has been indicated here in second diagram for the three-phase flux. We have three phases, three phasor. For each phase we have one phasor. So these three phases are at 120-degree from one another. Now this animated picture, as you see here, it indicates that the flux rotates in the air gap, right? So this is the air gap here, this is the air gap. So in this air gap we have rotating magnetic field which is produced by this three-phase stator winding. Now this rotating magnetic field is responsible for the rotation of a three-phase induction motor. Like in case of DC motors, in case of single phase induction motors, we make use of some starting methods, we make use of some starters, right? But in three phase induction motor, we don't have any such method. The three phase induction motor is self starting. Okay, as soon as a three-phase flux is set up in the air gap and this flux starts rotating in a particular direction, that depends upon the connections of the phase, right? It could be a clockwise or anti-clockwise direction, right? So as soon as this flux is set up in the air gap, the rotor of the induction motor, three-phase induction motor, starts rotating. So this we will cover in the next lecture when we will discuss about the operation of a three-phase induction motor. Today's purpose is to understand the concept of rotating magnetic field, how this magnetic field rotates in the air gap of a three-phase induction motor. So in this slide, we have covered the connections of a three-phase winding on stator and rotor, both of a three-phase induction motor. The connections could be star connections, delta connections, right? Here, as you can see, we have star connections. Then in second diagram, we have seen that this three-phase flux produces, this three-phase winding produces a three-phase flux. Now this three-phase flux is at 120 degree apart from one another and it is represented by three phases. And in the third animated picture, you can see that the flux is rotating in nature. So let us come to the next slide. So in this, as you can see here, this waveform represents a three-phase flux. So we have red supply the flux because of the red phase, that is phase 1, then yellow phase, that is phase 2, then blue phase, let us say this is phase 3. So either you can give notation as red, yellow, blue. This is one type of notation, or you can give 1 2 3 x y z p q r, right? It is totally up to you. Fine, but the standard global notation which is accepted, which is used, is red, yellow, blue for three phases. Now the first phase, basically it produces a flux which is given by phi r is equal to phi m sine omega t. Now because we are taking red phase as the reference, because it is starting from the origin here, and this yellow phase is, you can see it is, yellow phase is 120 degree lagging the reference phase, that is red phase. Okay, similarly you can see this blue phase. So blue phase is further 120 degree lagging the yellow phase. So the phase difference between red and yellow phase, or red and yellow flux, is 120 degree. And similarly phase difference between yellow and blue phase or flux is 120 degree. So you can say that this blue phase, or the flux because of this blue phase, lags the red phase by 240 degrees. This we have already covered in unit number 2, wherein we discussed about three phase connections, three phase AC circuits, right? Now we have three flux because of three phases. Phi r is taken as a reference, so it is phi m sine omega t. Then phi y is 120 degree lagging the red phase, and it is given by phi m sine omega t minus 120 degree. Then similarly we have phi b, which is phi m sine omega t minus 240 degrees, right? Now this three phase flux produces produced by the three phase supply, and this three phase flux has a rotating nature. It rotates in the three phase induction motor. Now when it rotates, it cuts the conductors which are placed on the rotor. You let us understand this with a diagram. For example, this is the stator part, right? This stator has three phase winding, right? So this three phase winding produces a three phase flux which is rotating in the air gap. And then we have a rotor here. This rotor has some conductors. The construction of rotor could be a cage type construction or wound rotor type construction. Fine. So when this uh, flux rotates in the air gap, it cuts these conductors. Now these conductors are connected to one another back to back, right? So they are shorted like this. Conductors are shorted. When cuts, this flux cuts these conductors. So these conductors will have certain EMF induced on them. Now this EMF is given by Fleming's uh, as per Faraday's law of electromagnetic induction, right? And its direction is given by Fleming's right hand rule. Okay, so now this three phase flux, as you can see here in this three phase waveform, at zero, we can take some certain cases of this to understand the rotating nature of the three phase flux. At zero, you can see this red flux is zero, this blue flux is positive maximum, and this yellow flux is negative maximum, or negative, not maximum, positive and negative. Similarly, at some point one where this is 0 degree, this is, let us say, omega t is equal to 30 degree, then this is omega t is equal to, for example, some 60 degree, then this is 90 degree, then this is, let us say, uh, some 120 degrees, right? This is 120 degree, this is 90 degree, this is 60 degree, and then 30 degree. So at 30 degree, this one, you can see that this phi m is positive, phi phi r is positive, phi B, blue phase flux is positive and yellow flux is negative. Then at 60 degree, blue flux is 0, yellow flux is negative, and red flux is positive. Then at 90 degree, you can see red flux is maximum positive, blue and yellow flux are negative. Then at 120 degree, this yellow flux is 0, red flux is positive, and blue flux is negative, right? So that means at a point of time, we have a resultant of these three fluxes. For example, at zero, you can see the resultant would be the phasor sum of these three flux. Like blue flux is positive, red flux is zero, and yellow flux is negative. So we have a resultant of all these three flux phasors, or we can say we have a phasor sum of these three fluxes. Similarly, at omega t 30 degree, red and blue flux are positive, but yellow flux is negative. Again, we will have a resultant of these three. So we will see that this resultant will have a certain value, it will be constant, it will have a certain direction. Okay, now let us see what would be the direction of this and what is the magnitude of this flux, resultant flux. Now at omega t is equal to 0, if we put omega t is equal to 0 in these three standard equations of these three flux, right? So we will have that the result, red phasor, this red phasor flux phi r is 0, phi y is minus under root 3 by 2 phi m. It is simple trigonometry, right? So phi b is root 3 by 2 phi m. So now you can relate these three values with the values at 0 degree, right? So at 0, phi r is 0, yes, it is 0. Phi y is negative, yellow is negative, yes, it is negative here. And phi b, blue, is positive, which is root 3 by 2 phi m, right? Now if you see that we have these three values, one is 0, one is negative, one is positive, so it seems that the resultant should be 0, but it is not like that. In this case, we will apply parallelogram law of vector addition, right? So in this diagram, you can see, for example, at omega t 0, we have a red phasor which is 0, which is not indicated here. We have a yellow phasor which has a value minus root 3 by 2 phi m. We have a blue phasor flux which has the value root 3 by 2 phi m. Now if we apply parallelogram law of vector addition, parallelogram law of vector addition, right? So if we use this particular law, so we will get that the resultant phasor is 1.5 phi m, where phi m is the maximum flux. It is the maximum flux, right? So, and it has a direction. So you can see the direction of this flux, the resultant phasor is downward here, like this, fine. So Now let us see what happens if we take omega t is equal to 30 degree. So if omega t is equal to 30 degree, if we put omega t is equal to 30 degree in the standard equations which are given here, so we will get that phi r, which is the flux of red phase, is 1 by 2 of the maximum flux phi m. Similarly, phi y, which is the flux of yellow phase, is given by minus phi m. And then phi b, which is the flux of blue phase, is given by phi m sine minus 210 degree, which is 1 by 2 phi m. Now, if you add these three, simply add these three, you'll see that it seems to be zero, but it is not zero because we do not use a simple addition here. We use parallelogram law of vector addition because these three are vectors which are represented by vectors. In the first slide we have seen, in the very first slide we have seen that these three are vectors, phasors, right? So we will add them using the given law. So here as you see, this red phase is 1 by 2 phi m. So it is shown here red phase. Then we have a blue phase which is 1 by 2 phi m. Then we have a yellow phase. So we have all these three phases here, right? Now we will use a parallelogram law of vector addition by using these two vectors, phasors, right? Phi r and phi b. So the parallelogram, by using the parallelogram law of vector addition, the resultant which is obtained is phi r 1.5 phi m. So this would be the resultant. You can apply this law and you will get the answer. Now the resultant is this one and it has a direction. It now, if you see this, the direction is this one. Now if you compare this with this direction where we took omega t is equal to 0, so at omega t is equal to 0 the direction was like mm, bottom down, right? Then we have at omega t is equal to 30 the direction is this one. Now if we compare these two, earlier at omega t is equal to 0, so the direction of resultant was this one. Now it is shifted in this side. It has, the resultant has shifted towards clockwise direction. Now what it means, it means that, as I discussed in the beginning, that because we have a three phase supply, because of this three phase supply we have a three phase flux. So at any point of time we have some values of these three phase flux, right? We are representing them with phasors. So every phasor will have a magnitude, a value. By putting the value of omega t equal to that particular angle value on the time axis, right? Now the resultant has certain value, certain magnitude. Now this means that though it seems, though it seems that if we simply add these three values, 0, let us say minus 3 by minus under root 3 by 2 phi m plus under root 3 by 2 phi m, so it seems that a simple addition will give you a zero answer. Similarly, here also the simple addition will give you a zero answer, but it is not zero. It has a magnitude, and magnitude as well as it has a direction. Now, direction is that it is moving in the clockwise direction. That means the resultant phasor is shifting towards clockwise whenever we are increasing the angle by 30 degree or by any value, right? This is just to make the thing simple. We have taken the angle 30 degree. You can take 0, 15, 30, 45, 60 like that. Fine. Then if we put omega t is equal to 60 degree, then what happens? At omega t is equal to 60 degree, the value of flux because of red phasor or red phase will be under root 3 by 2 phi m. Because of yellow phase, it is minus under root 3 by 2 phi m. And because of blue phase, it is 0. So you can see here in this particular diagram, here we have a red phasor, we have yellow phasor, but we don't have blue phasor because the value of blue flux or the flux because of blue phase is uh, 0. So again, we will use the parallelogram law of vector addition here, right? So by using the parallelogram law of vector addition, we'll get the answer, which is phi r is equal to 1.5 phi m. So now if you compare this direction of this particular resultant phasor, which is obtained by putting omega t is equal to 60 degree, so you will see that this phasor has further moved towards or shifted towards clockwise direction. So we started from here. We got a phasor at this point for omega t 0. This is for omega t is equal to 30. This is for omega t is equal to 0. So what we are seeing? We are seeing that the resultant phasor is moving in the clockwise direction. So there are two things. One is this resultant has a magnitude which is constant. For all these three values of omega t, 0, 30 and 60, the resultant phasor is constant, 1.5 of the maximum flux. However, it has a direction. That means it. Let us put omega t is equal to 90 degrees. So when we put omega t is equal to 90 degree in the standard equations of these three fluxes, so for phi r, the value would be phi m because sine 90 is 1, and for phi y it is minus 1 by 2 phi m. For phi b it is uh, we have minus 1 by 2 again phi m, right? So again, if we add them simply, if we do a simple addition, it seems that the resultant would be 0. But again, we will apply the parallelogram law of vector addition, right? So by using parallelogram law of vector addition, we will get an answer which is phi r is equal to 1.5 phi m. Now again, you can see we started from this point where we had omega t is equal to 0, then omega t is equal to 30, then omega t is equal to 60, then omega t is equal to 90. So this is omega t is equal to 60, this is omega t is equal to 30, and so what we are seeing, what we have observed, that this resultant phasor is moving in clockwise direction, and it is moving with this omega means this is in radians per second, right? So this would be the angular velocity of this particular phasor. Now it has magnitude which is constant for all these four values. Similarly, if we take omega t is equal to 120, we'll get this one. If we take omega t is equal to 150, we'll get this one. If we take omega t is equal to 180, we'll get this one. So what we are observing, that it is moving. So this resultant phasor is moving. This resultant phasor is nothing but it is the net effect of these three fluxes. So let us come back to the first slide. So in first slide, in this slide, if you see, we have this three-phase flux represented by this three-phase waveform. So at any point of time, we will have the net effect of the three fluxes, phi r, phi y, and phi b. So this net effect is shifting in clockwise direction with every increment in the value of omega t. So starting from omega t is equal to 0, then let us say omega t 30. So for simplicity, we have taken 30 and 60 and like that. We can take any value of omega t. The answer will be same, the answer will not differ, right? Even if you take the value of omega t is equal to 10, 0, 10, 20, 30, 40, 50, 60 like that, even then the resultant phasor will be phi r is equal to 1.5 of the peak flux, maximum flux, right? And its direction would be in the clockwise uh, round, right? So this shows that we have a flux which is produced by a three-phase stator winding in a three-phase induction motor, which rotates at a particular speed. Now this speed is basically known as synchronous speed. We will discuss this in our next lecture. Though this speed, it has a certain mathematical expression also. Now we have taken all these four cases in a single diagram here, right? Like this and here like this. So here we have omega t is equal to 0, then 30, then 60, then 90, and you can see that this resultant phasor is shifting with the value of omega t. Now this shifting nature of the flux, three-phase flux, okay, is known as the rotating magnetic field. So it seems that the magnetic field is rotating. However, it is the effect of the three fluxes, the net effect of the three-phase flux, which is shifting its position in the space with omega t, right? So the net effect shifts. Because of this, we say that we have a field, magnetic field, which is rotating in nature, and this rotating magnetic field becomes the base of the operation of a three-phase induction motor, which we will discuss in our next lecture. So this is it for today's class. Thank you so much.